Hello. So, for acetylsalicylic acid, we want to know the molar mass. So we take the mass of carbon, which is 12.01, multiply that by 9, add that to the mass of hydrogen, which is 1.008, multiply that by 8, add that to the mass of oxygen, which is 16, and multiply that by 4, and we add them all up together. 12 times 9, okay, so the total for the carbon is 108.09, and we have 8.064 for the hydrogen, and just 64 for the oxygen. If we add these all together, 64 plus 8.064 plus 108.09 is 180.154 grams per mole, and that's the molar mass of aspirin. Here we have the structure for acetylsalicylic acid, and if we want to know what the geometry of each particular atom is, we can calculate the steric number. And I am just going to put those little subscripts there to kind of differentiate between the carbons. So, and we can also keep in mind that if the steric number is 2, the hybridization is sp, and the geometry is linear. If it's 3, the hybridization is sp2, and it's trigonal planar. Now, if the steric number is 4, then it's sp3, and it's tetrahedral. And we can calculate it by adding the lone pairs to the number of atoms it is bonded to. So let's start with this one. For carbon 1, we have 3 atoms it's bonded to, no electron pairs, so the steric number is 3. So it's sp2, and it's trigonal planar. And actually, we can kind of look at all of them: C1, C2, C3, C4, C5, C6, C7, C8, C9, and they're all the same with their geometry. For O1 is a little bit different, I think. O1 has 2 electron pairs, and it's bonded to 1 atom. So it still has a steric number of 3, so it's still sp2. O3 is also sp2 because 2 pairs, 1 atom is bonded to. Now O2 and O4 are a little bit different because you see they have 2 electron pairs, and then they're also bonded to 2 atoms. So they are sp3, and they're tetrahedral. So we want to count the bonds. So we have to keep in mind that a single bond is 1 sigma bond, whereas double bonds are a 1 pi and 1 sigma bond. So we have 1, 2, 3, 4, 5 double bonds, so that's 5 pi bonds and 5 sigma bonds. And we could count all the single ones: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's 16 single bonds. But 16 plus 5 is 21. So we have 21 sigma bonds. 21 sigma bonds, 5 pi bonds. Now we want to know which ones of these oxygen have delocalized electrons. So the way I see it is we have 2 pi bonds that are delocalized, that are outside the main chain right here. So these ones, O1 and O3, are going to be where we have the delocalized electrons, because we have delocalized pi bonds. So acetylsalicylic acid is a little bit soluble in water. It's because of these OHs, the OH right here, and the double bonds on these oxygens right here, which allows it to hydrogen bond with water. But this part right here, the large hydrocarbon chain, kind of hinders that, so they kind of go against each other with the solubility in water. So I thought I would jump ahead and explain why this is an acid. So we see this COOH, which is I guess a carboxyl group, and this is the part that's responsible for it being an acid. And some properties of acid is that it turns a blue litmus paper red. It has a sour taste. It will corrode metal, and it releases positive hydrogen atoms into a solution. And of course, it has a pH that is below 7. Mass percent of a human is typically 60% water. And suppose we have somebody who's 160 pounds who ingests 325 milligrams of acetylsalicylic acid, or aspirin. And we want to know what is the concentration of that in moles per liter for this particular problem. So we assume, okay, so we have 160 pounds, and we're taking 60% of that, so we can multiply by 0.6 or whatever, or 3/5, or but at the end we get 96 pounds. And then we know that 1 pound is equal to 453.59 grams. So we can multiply 96 by this 453.59 grams conversion factor, so that 96 pounds is equal to 435.59 grams. That's not right. Sorry. I misread my notes. So it's 435.44.64 grams. And because this is water, we can replace that with milliliters, because the density of water is just 1 gram per milliliter, or it's basically the same. So, well, no, it is the same. And we know the mass of the aspirin. Well, we have 325 milligrams of the aspirin, which is 325 times 10 to the negative 3 grams. So put a little equal sign there. And then we know the molar mass. This is our human. And we know the molar mass of aspirin is 180.5 158 grams per mole. So now we're going to divide this by that. And to find the number of moles, so moles is going to be equal to 325 times 10 to the negative 3 divided by 180.158, which turns out to be about 1.8 times 10 to the negative 3 moles. But we want to know the concentration of this in here. So now we're going to do 1.8 times 10 to the negative 3. Divide that by 434.64 milliliters. And this is, of course, moles. And this gives us moles per milliliter, but we want to know moles per liter. So we can multiply this one by 1,000. 1, 2, 3. Now we can kind of cross that out. So we have just liters. And 1.8 divided by 1,000. Divide that by 43.54464. And we get about 4.13 times 10. No, that's an awful 10. 10 raised to the negative 1, 2, 3, 4, 5. Negative 5 moles per liter. And that's it.